Everyone, I'm Ruiquan. I'm going to talk about high to low dimensional PPA completeness, which has applications in many natural problems like Borsuk-Ulam, Tucker, consensus halving, and ham sandwich. This is based on my joint work with Alex and Abiyat. In this talk, I will start with the ham sandwich theorem and the complexity class PPA. Then I will talk about the techniques we use in this paper. Finally, I will briefly mention the consensus halving problem and our results on it. Suppose that we have three types of toppings on a ham sandwich. Then the ham sandwich theorem states that there always exists a class that equally partitions all three toppings. This theorem also generalizes to higher dimensions, where on a d-dimensional space with d toppings defined by d-density functions, there always exists a hyperplane that cuts each topping into two equal parts. More generally, we can go beyond this additive case. The generalized ham sandwich theorem says that for any d Lipschitz continuous set functions, there always exists a hyperplane partitioning all set functions into equal parts. For this wonderful existence theorem, as a computer science, we would ask if we can efficiently find such a solution. Unfortunately, the answer is no, unless PPA is a subclass of FP. Here, FP is the class of all such problems that can be solved in polynomial time. And we will introduce the class PPA slightly later. Further, we may care about these computational questions. What happens if we allow extra hyperplanes to cut the space? Or what happens if we only need to have P out of the D functions? In fact, in our paper, we prove that it remains PPA complete to use K hyperplanes to approximately equally partition at least 2 out of D general set functions, or 3 out of D monotone set functions, once here K and D are constants. Next, I will briefly introduce the computational class PPA, whose full name is polynomial parity arguments. Given a circuit defining a graph with degree no greater than 2, and we are also given one node with degree exactly 1. The objective is to find another node with degree exactly 1 in the graph. For example, here, the blue node is given by the input, and all these 3 red nodes can be feasible solutions. Famous members of this class include Nash equilibrium, factoring, Borsuk-Ulam, and Tucker's lemma. Among them, the Borsuk-Ulam theorem is used to prove the ham sandwich theorem. The Borsuk-Ulam theorem says that for any odd continuous function f mapping from a d-dimensional sphere to d real values, there always exists a point on the sphere with all function values equaling to 0. One interpretation of the 2D Borsuk-Ulam theorem is that there are always 2 antipodal points, or say 2 points on the opposite side of the Earth that have the same temperature and humidity. This theorem has a lot of interesting applications in game theory and combinatorics, including the existence of consensus halving, necklace splitting, and the proof of Nether's conjecture. In fact, in Matosak's 200-page book, there are more such applications. Using the Borsuk-Ulam theorem, the proof sketch of the Ham-Sandwich theorem is as follows. We can first normalize parameters in each hyperplane so that each hyperplane can be represented by a point on a d-dimensional sphere. By the hyperplane, we can easily represent the two parts in the partition. Then we define the ith function by the difference of the set functions for the two parts. These new functions are odd because the two parts just swap if we reverse the sign of the parameters. By the Lipschitz continuity of the set functions, these functions are also continuous. So we can use the Borsuk-Ulam theorem to show that there always exists a group of parameters where the induced two parts are equal on every set function. To establish the Borsuk-Ulam theorem, there is a famous combinatorial lemma, Tucker's lemma. In a Tucker's coloring, we have triangulation of k-dimensional ball and the coloring of the triangulation with 2k colors, plus or minus 1, plus or minus 2, up to plus or minus k. And this coloring satisfies the antipodal antisymmetry on the boundary, which means that for any point x, x and minus x are colored by opposite colors. Then, Tucker's lemma says that in any Tucker's coloring, there always exists a small complementary edge, which is one simplex in the triangulation that contains a color plus c and minus c for some c. By the previous work, it has been shown that it is PPA complete to find such a solution for any k greater than or equal to 2. In our paper, we consider a relaxation of this lemma. Given Tucker's coloring with plus or minus 1 and plus or minus 2 on a k-dimensional space, our goal is still to find a complementary edge. This relaxation seems computationally easier because solutions can be everywhere in a space. That is, for any 2D slice whose boundary consists of antipodal points on the KD boundary, then there is a solution on this 2D slice. However, our main technical result shows that this relaxation remains PPA complete. This has a direct implication for a relaxed Borsuk-Ulam theorem, where given a high to low dimensional odd continuous function, it is PPA complete to find a point that has two values approximately 0 on the sphere. The number of dimensions can be arbitrary constant above 2 here. So this implication can be very useful to prove the hardness of the relaxed generalized Ham-Sandwich problem. Intuitively, the k-hyperplanes can create k times d non-trivial parameters, which correspond to m here. And there are d-set functions which correspond to n here. Also here, the number of 2 corresponds to the number of set functions that get equally partitioned. So now here, everything we need to prove our previous PPA completeness of the generalized Ham-Sandwich problem is covered here. Technically, our paper is similar to a previous work where an approximate version of Sperner's lemma is shown to be PPAD complete. The paper also has very intriguing applications for the n-weak free k-cutting problem in game theory. Next, I will briefly talk about the techniques we use to prove the hardness of approximate Tucker. Formally, we will use two different versions of approximate Tucker. The first one, as used by all previous works, is defined on discrete L-infinity balls. More specifically, the coloring is mapping from k dimensions of integers between -n and n to +or-1 and or plus or -2. The goal is then to find 2 points with L-infinity distance bounded by 1 that has opposite colors. For k equaling 2, it is the same as the original unrelaxed Tucker problem and has been shown to be PPA complete. The second one is defined on continuous L2 balls, and the goal is to find 2 points in the continuous space with L-infinity distance bounded by some epsilon that had opposite colors. We will show PPA completeness for all these versions with k greater than or equal to 2. Our reduction will be 3-step. We first reduce the 2D discrete instance to the 2D continuous instance. Then we lift up the number of dimensions for the continuous version, and finally reduce back to the KD discrete version. The first and the third step are fairly simple, using mappings between L-infinity and L2 balls, which preserves the distance by a factor of poly k. From this picture, you can briefly see how the transformation from the discrete case to the continuous case work. Next, we will focus on our techniques for the second step on k equaling 3, because this idea can be generalized to higher dimensions. For the first step of our construction, we give a preliminary coloring on the sphere of the 3-dimensional ball. We observe that we can simply project the upper hemisphere to a circle in order to get a 2D instance. If this 3D instance is hard, the projection should be as hard. So intuitively, we should use a 2D PPA hard instance on the upper hemisphere. Then we observe that the upper and lower hemisphere share the same boundary, which both correspond to the equator of the 3D instance. In order to get the coloring on the lower hemisphere, we can simply rotate and negate the coloring for the upper hemisphere. So up to now, we get a preliminary sphere coloring. And also, this is easy to observe that it is PPA hard to find a solution restricted to the sphere in this preliminary coloring. Then, in the second step of our construction, we cut the 2D instance. We define the feature C radius for every color by a point RC on the circumference, such that the color of the point equals to C. And this step can satisfy antipodality where RC is antipodal with R minus C. Then we define C1, C2 sector as a small sector between RC1 and RC2. Because we won't use the case where C1 equals to C2 or minus C2, here we only consider the case where C1 and C2 have different absolute values. With this definition, we can either find all featured radial sectors or a solution on the circumference of the 2D instance in polynomial type. The final step of our construction is to color the interior of the ball based on the preliminary coloring. We define color switch as one simplices where there are two different colors in the neighborhood. For example, here, this is a -1, -2 color switch. Then the interior coloring of each point depends on its projection to the sphere. Or say, we are coloring each radius of the ball. Then we discuss how this projection locates. For the first type of projection, which is far away from any color switch, we will simply use the C radius, where C is the preliminary color of the projection. For the second type of projection, which is close to a color switch, we consider a small line perpendicular to the color switch with different colors. Then this line induces this sector with the center of the ball. For this entire sector, we will use the corresponding feature sector to color it, which is chosen based on the preliminary colors of these 2 points. Note that here we may change the preliminary coloring on the sphere because this featured sector may have very complicated boundary. However, antipodal antisymmetry of this 3D instance is still preserved, while the antipodal antisymmetry of the 2D instance we have. In addition, one detail here is the case that in the color switch, the 2 colors are opposite to each other. We don't define feature sector for this kind of 2 colors earlier. However, it is not a problem because if there are 2 such points, it corresponds to a solution restricted to a sphere in the preliminary coloring, which is PPA hard to find. So it does not hurt our reduction. Finally, in this talk, we will briefly talk about the consensus halving problem. The problem definition of consensus halving is as follows. There is an interval from 0 to 1 and n agents, each with a valuation over subsets of the interval. The goal is to cut the interval into n+1 pieces and partition it to 2 parts, so that the 2 parts have approximately equal valuations for all n agents. Using the Borsuk-Ulam theorem, we can show that this kind of cut and partitions always exists even for epsilon equaling 0. As another application of our approximate Tucker, we show that for any 2 or more agents with general valuations, it requires Pauli epsilon inverse manicuries to find a solution even with any constant number of cuts. Similarly, for 3 or more agents with monotone valuations, we show a very similar pure complexity lower bound. Similarly, as earlier in this talk, this hardness also works for the case where we only want 2 or 3 agents to be satisfied, depending on the type of valuations. For conclusion, the main takeaway message for this talk is that although some topology theorems give direct corollaries in a high to low dimensional manner, they don't actually reduce the computational complexity. Here, for the Borsuk-Ulam theorem, it's still hard to find zeros if the function is mapping from a 100 dimension to a 2 dimension. Then we have a lot of applications from this PPA hardness. We show that for ham sandwich theorem and the consensus halving, it is as hard for more cars, fewer satisfied agents, and for ham sandwich, even the more dimensions is still as hard. However, our method does not work for additive valuations. It only works for general or monotone valuation. So we still leave the open problem for consensus halving and the ham sandwich where the valuation is additive. And this open problem both remains here for a constant number of agents or a large number of agents. That's all. Thank you.